Hi, welcome to this particular module. In this module, we will look at the characterization techniques for understanding the thickness of silicon dioxide. So, there are three basic characterization techniques. One is called the surface profilometer. Second one is just observing the silicon dioxide with a naked eye and looking at the color, and third one is called the ellipsometry. So, we will be looking at these three techniques and then we will also look at one of the PVD technique which is called thermal evaporation, alright. So, if you see the slide you will see that there is a surface profilometer, and this surface profilometer will help us to understand the thickness of the silicon of the silicon dioxide or any other material deposited on silicon wafer. How can we know that? Suppose this is a silicon wafer, right. I am growing a silicon dioxide using thermal oxidation, which you have seen in the last lecture, and then I am patterning this using a photolithography to form the steps, this particular step, alright. Now, if I use this stylus profilometer, then what will happen? The stylus will start moving from this and it will come here. When it comes here, it will create this step. So, this height can be measured with the help of stylus profilometer. What is the disadvantage of this particular system? This disadvantage is that we need to destruct the silicon or the layer that we have deposited onto the substrate. What does it mean? That now I have silicon dioxide everywhere, but in this case I have to pattern it so as to get the height of the material deposited onto the silicon wafer, right. So, these are destructive technique because we cannot keep our film intact. For example, if I have oxidized silicon wafer like this, alright, and I have my aluminum everywhere, let us say aluminum is everywhere here like this. Now, I want to know what is the thickness of this aluminum. How would I know? I can only know when I create a step. So, for creating step I have to etch my aluminum in this particular fashion, so that I will load my stylus, it will move and it will come here, and this will give me aluminum height. But here I am etching aluminum from this part, and that is why it is called destructive technique, alright. This is what I mean by destructive technique. Here you can understand the thickness of any material with the stylus profilometer. It is a diamond tip in a easier manner, right. Here if they have shown that HF you can use for etching silicon dioxide. The first example that I took here, while aluminum you can use aluminum etchant to etch the aluminum. We will be looking at this in detail. The second technique which I was talking about is with the help of constructive interference. This will be we can view from the above, and that is what I was showing it to you. If you see the wafer, again I am holding in my hand, then you will see that the color of the wafer is different, right. So, the color of the wafer, depending on the color of this wafer, you can say that what is the thickness of silicon dioxide. This is a constructive interference, and on 1 hour I can tell the color difference between two films having approximately 10 nanometer difference, alright. But that is true only when you are an experienced user, alright. So, the best way is to use a tool. This is where you do not have the tool, is approximation. Approximation does not work in real life domain. You need to be accurate when you want to devise or design or fabricate a sensor, because the performance of a sensor will depend on the accuracy of the insulating material. But in some cases the insulating material is just used as an silicon dioxide is just used as an insulating material between two layers, and it does not matter if it is 1 micron or half micron or 250 nanometer. In that case you can just use your eye to understand whether silicon dioxide is there or not. Okay. So, if you see the slide again, the like I said, our eye can have the can measure the color difference of about 10 nanometer thickness, and you can see here the relative intensity, illumination intensity versus film thickness. As the thickness increases, the film becomes dark green in color, right. For the thin film, it is close to your light gray, which is close to silicon wafer. All right. The third technique is ellipsometer, and your homework is to understand what is the use. So, if you see here, the light source is there, filter is there, polarizer, quarter wave plate, and it reflects back, and there is analyzer and detector, right. So, you need to understand the function of each part, and that is your homework. What is the function of polarizer? What is polarizer? What is a quarter wave plate, right? What can be analyzer? What kind of analyzers are used for the ellipsometer? The advantage of this particular technology is that after quarter wave plate, the linear polarized light becomes circularly polarized, which is incident on the oxide cover wafer, which is this one, and the polarization of the reflected light, which depends on thickness of refractive index of the oxide layer, is determined to use to calculate the oxide. The advantage, further advantage, is that this ellipsometer is extremely accurate with an accuracy of about 1 nanometer. So, this is perfect for a lot of application. Multiple wavelengths incident angles can be used to measure thickness and refractive index of each film in a multi film stack. That is another point that you need to remember. Like I said, your homework will to understand what is the role of polarizer, what is the role of quarter wave plate, what is the role of analyzer, and what kind of detectors are there. Similarly, what kind of light sources and filters are used. This will be your homework. Now, let us go to your first technique, which is a physical vapor deposition technique. I have explained it to you in earlier classes how the thermal evaporation works, right. Let us in this class see the video of the thermal evaporation. As you can as we have seen earlier, these are the substrate source holders, right, and when you load the source between between one of the source holders, let us say between this and this, if I load a source, right, then what will happen? When I heat it, it will evaporate. This is what is shown exactly here, right. This is a substrate holder, and you have different kind of substrate, you can load it here, right. Generally these substrates are kept at 90 degree with respect to the source, and it is not kept loaded here or here. The reason is because if you look at the cosine law, the maximum deposition will occur when the surface when you keep the wafer at 90 degree or in line with the source material. So, if I want to show you how the thermal evaporation unit works, let us play this video.
OLED stands for Organic Light Emitting Diode, a special layer that glows when an electric current is introduced. Consumers are demanding better display. OLED displays satisfy that demand. They are brighter, lighter, thinner, and consume less power than LCD displays. OLED is superior than LCD. When you buy a cell phone these days, these phones usually have an OLED display. This is where you can see the big advantage offered by OLEDs. They provide very high contrast. OLED displays also very flexible. OLED also apply to organic solar cell that provide mechanical flexibility and choice of colors. OLED manufacturing can be classified into two categories, which is dry and wet. The dry manufacturing method refers to the conversion of raw organic material from solid powder formed into gas phase. This method called thermal evaporation techniques that also used in manufacturing mirror. Next video shows using mini thermal evaporator coater TH350. Thermal evaporation is one of the simplest of the physical vapor deposition (PVD) techniques. Basically, the material is heated in a vacuum chamber until its surface atom has sufficient energy to leave the surface. The application of thermal evaporation are in production of food packaging, optical components, spectacles, solar cells, semiconductor wafer, lamp reflector, and many more.
Okay, let me show you one more video where you can see the thermal evaporation system, how we can use it, and you will now understand that how we are using this video, how we are using the thermal evaporation unit to deposit several films. Okay. So, what you understand from this? If you can you understand that how the thermal evaporation unit works, and thermal evaporation unit is a part of physical vapor deposition technique, right. So, in the next class what we will be looking at, in the next class we will be looking at the E beam evaporation and subsequent the related videos for the E beam evaporation unit. Finally, we will also look at the sputtering and the video for sputtering. You see, I have brought you or actually I found interesting videos. There are a lot of videos on YouTube, but not every video would be really informative, and that is why I tried to put some videos from the YouTube, so that you can understand how the techniques that we are discussing in the theory class works, and how can you, how it looks like. We will also look at the E beam and thermal evaporation unit in our experimental class, so or a laboratory class. So, that will give you a better understanding of how can we use the system. So, till then you take care, I will see you in the next class.